to show a body executes simple harmonic motion, you need to show that its acceleration is proportional to minus its displacement from the equilibrium position. Now, the derivation for it is this. The first thing you need to do is look at Hooke's law, and that's the equilibrium position. So when you have a string that's got a particular length or a particular natural length, and you put a mass on it, the spring extends, and it extends down by a displacement. I'm calling that displacement S. Now what it does though is it comes to rest, so that means there's no net force acting on it. So the weight acting downwards and the force of the spring trying to go back to its original length, called the restoring force, they have to be equal and opposite. So that's what I have there. And what we'll notice is that F is equal to minus Ks applies, but I'm ignoring the signs here because these guys are in opposite directions. So if I did include the signs, it would still work out. Now bank that for the next step. Right, we'll come back to that. Okay, the second thing then is the body is pulled down a distance x below the equilibrium position, so that's that position, and then let go. So we have the natural length, the equilibrium position, and then it's pulled down. I'm saying it's pulled down a displacement or a distance x. In this case, the two forces acting on it are still the weight, and the restoring force I'm calling F2. F2 is larger than F. And the reason for that is, or the explanation behind it even, is if I leave that go, the object will accelerate up. So there's a net force between the two of those acting up, which is the difference between them. So let's apply F net equals ma. The particle is pulled downwards, so I'm going to say that's the positive direction. I'm going to say negative is upwards then. So mg minus F2 is equal to ma. F2, we'll apply Hooke's law to it, k times the displacement. So we have k, and remember the displacement for Hooke's law is from the natural length position. So it's from that height there. So when you pull it down that far, the displacement is actually s, which is the distance to get to the equilibrium position, and x, which is how far it was pulled down below the equilibrium position. So when you multiply in, you get mg minus ks minus kx equals ma, and I said bank that thing up there. Mg is equal to ks, so the two of those are equal. We can cancel them. We get minus kx is equal to ma, and when you divide under, you get a is equal to minus k over mx. So a is proportional to minus x, which shows simple harmonic motion, and that's the job done. Now there are two notes here as well that I want you to keep an eye on. First of all, if you compare that formula to a is minus omega squared x, it means that omega squared is equal to k over m. That's both in the physics course and the applied maths course. In fact, it's stated in the physics syllabus, so you do need to know that. So omega then is root k over m. And the second thing then, just as a bit of an aside, because people sometimes miss this, t is equal to 2 pi over w. If you put w in there, you get t is equal to 2 pi times the square root of m over k. So m is the mass of the object placed at the end of the spring. K is the spring constant.